Hi there, today we're going to be doing the first half of the Earth's Resources unit. It's a long unit, it's not difficult, but there's a lot of stuff in it. We're going to do the first half, and again, as with previous videos, I'll be stopping at various points and telling you now's a good time to pause and do certain questions from the master booklet, which you can either get on Moodle or if you email the school to ask me for them. We're going to be looking at the Earth's resources. Now, resource is something that we use for anything, and typically we think about warmth and shelter and food and clothing and our cars and our smartphones and everything that we use. Now, in order to make that thing, we have to use a resource. It has to come from somewhere. So some nice examples. In the top left, there's a metal. So some metals, as we know, exist as pure metals in the Earth's crust, but most need to be extracted. And we use metals for all sorts of things: circuitry, construction, manufacture, all sorts of things we need metals for. We've got glass over there, which again we need to make ourselves, bricks, which we use for houses, timber or wood, which we use again for all sorts of means. And if you just think about the common house and all the stuff that goes into it in terms of the resources that we need to take from the earth, it's really, really quite extensive. Now, there's some keywords that we need to be able to use. First is the difference between a natural and a synthetic item. So a natural object or article is something that exists naturally. So an apple is a good example. It grows on a tree. You don't necessarily have to do anything. It's going to grow there anyway. And here is this is a joke by the way, that's a synthetic apple. That's an apple that has been made by human beings. Again, made out of various materials that will have been extracted at some point from the earth and processed and changed and turned into something else. We need, a lot of time we're running out of stuff, and where we get things from natural sources, we're running out, there's not enough of it left. So a lot of time we're looking to make synthetic replacements of things that we would otherwise have got naturally. So some examples are that we replace wool in clothing with acrylic fibre. Now, why would you do that? Because wool has to come from sheep. Now, sheep are great, but they need a large amount of space in order to live. Do we have that space? Well, we're running out of space. So maybe it's easier if you can make a small factory and start making acrylic fibre instead. Similarly, cotton, which requires, again, plants and insects and things, I don't really know about, is now being replaced by polyester. And even wood, timber, we now replace with PVC, which is a type of plastic, or an MDF composite, which is it's basically a special type of wood that's made from wood shavings altogether. And triple scientists will learn more about MDF later. A really nice example is the replacement of crude oil with biogas or biofuels. So crude oil, as we know, is running out. It's a finite resource. It's going to run out. We don't have an endless supply of it, but we need it to power our cars and to power our homes and our televisions and our transport methods, everything we need crude oil for. It's running out, so a lot of countries now, they are making fuel from organic products. So you grow certain types of corn, and depending on how you process that, you can turn it into oil. The same applies in places like Brazil. They turn cane sugar into bioethanol, which you can then just pump straight into your car and use instead of fuel. So you can just grow a massive field for the sugar, chop it down and process it in certain ways, and you end up with a nice fuel that can be used to power cars instead of using crude oil. This is a nice little graph that you can find in your textbook, which is on Caboodle. Now, you don't need to know any of this off by heart, but it shows what will happen to the amount to the resources that we use if we keep using them at the same rate. So the graph on the left shows that if we currently produce things at the current rate, so if we're producing X amount of things every year this year, and we keep doing that every year, and increasing as we are currently doing, then, so for example, gold will be depleted by 2027, there'll be no gold left by 2027, there'll be no natural lead left in the earth by 2031, silver, tin, same applies. We'll have about 18 more years of oil. And that graph is if we stop at current levels. So if we're, say, using 100 tons of oil, we're using way more, but if we were using 100 tons of oil a year now, and we kept that 100 tons every year until 2036, then in 2036 we'd only have 18 more years worth of oil. But if we keep going the way we're going, so what that means is that last year they might have used 90 tons of oil, this year we're 100, next year it might be 110. If we keep going that way, there'll only be 11 more years of oil left so it will be gone by 2050, and almost all of the substances that we take out from the earth, so cadmium, which we use in electronics, gold, graphite, lead, silver, tin, all of that stuff will just be gone. So we really are running out. There's not a lot of this stuff left, and it's not going to go on forever, which means we need sustainable development. And those of you studying geography will already know about sustainable development. The technical definition is development is where we can meet the needs of current generations without compromising future generations. So it means that we can feed and provide shelter and clothing for the current generation, but without compromising future generations. So that future generations won't turn around and say, well, we've got nothing left, how are we supposed to function and live? So it's really important that we need to do sustainable development. And at this point, you can do questions 1 to 8 in your booklet. Once you've done questions 1 to 8, we'll look at water safe to drink. Part of this unit is about an incredibly important resource for us, water. We need water in order to function. Without water, we will dehydrate and die very quickly. And we need specifically water that is safe to drink, because it's not as straightforward as you'd think. And there's a lot of thought, a lot of time, a lot of science that goes into the water that comes out of your tap. So most of our water comes originally from condensation and rain. So when we studied the Earth's atmosphere, we learned about how the Earth originally was this big hot ball of hot rock, and any water that was there would have been as a gas, water vapor. As time goes on, the Earth cooled down, and it got, once it hit below 100 degrees, all of that water could condense and rain, and that's what's filled up our rivers, our seas, and our lakes and oceans. There are a number of different places where we can get natural water from. Rivers, the sea, this is a well, so wells just dig down into the earth, and there's a lot of water kind of absorbed deep into the earth, and what the well does is it sucks all that water out, not by any physical process, it just naturally comes out of the rock. And then at the top we've got a dam and an artificial lake, so that's where you build a big wall in front of a river, and everything behind it floods up and fills with water, what's called a reservoir. Water's not always safe to drink. I would highly recommend you don't drink water when you're just wandering around the countryside. So everyone knows you don't drink seawater because it's full of salt, it's not good for you. If you drink seawater, not only will you throw up, but it'll kill you. You can't drink too much of it, you'll just die. Now obviously you can still go swimming in the sea, and if you swallow a bit of water, that's not the end of the world. But if you drink nothing but seawater, you will die very quickly. So you don't want to do that, ever. There are also problems with certain microbes and other harmful chemicals that might be around. So this is a picture of Sir Steve Redgrave and his rowing partner. So Sir Steve Redgrave is a highly decorated British rower, and this is his partner who's called Andy Holmes. Andy Holmes died a while back of something called Wales disease. Now Wales disease is from drinking river water normally that's been contaminated naturally, normally by things like rats urinating in the water, and it can carry an infection which will make you ill and die. So the water even in rivers isn't safe to drink. So almost everyone knows that seawater is not safe to drink, but even river water from lakes is not necessarily, straight off the bat, safe to drink. So what we need to do is we need to turn that water into a form whereby we can drink it without getting ill. Scientists call that water potable water. Potable water is water that is safe to drink. It's not pure water, there's still other stuff in it, it's just safe to drink. If you take a bottle of mineral water, for example, like Evian or whatever, on the back of the label it tells you all the stuff that's in it, all the minerals, calcium, magnesium, sulfates, all of the stuff in it that's good for you, it helps your bones, it's good for your natural growth. And the same is true of our tap water, it's got minerals in it, but it's safe to drink. So we call it potable water. It's not pure water, it's not water and nothing else, it's just water with only stuff that is safe to consume. Question is, how do we get it? So first thing we need to do is we need to choose a source of water. Normally, at the moment, we'll get onto seawater in a second, we're talking about rivers, lakes or wells. First thing you do is you filter it to remove large objects. So you actually pass it through like this big grating with like these metal, it's like a fence almost. And anything that's big, like a branch or any rubbish that people have thrown into the water, or any dead animals or whatever, they get caught by this big kind of screen, this big filter with these big metal bars. You get rid of a large object, and then what you do is you sterilise it. Sterilising is the process of killing any microbes, so any bacteria that are in there, and generally we use chlorine, ozone or UV light. All of those things are very bad for bacteria. Now later on in the process, so when you put chlorine in, for example, chlorine is toxic to humans as well, but you put enough chlorine in that it harms the bacteria, but it's not going to be a problem for us. And ozone and UV light, so ozone is a gas, so it'll go away anyway, and the UV light is just when you shine UV light on it, it'll just kill everything in there. And then you can drink it, and then you can do questions 9 through 16. Okay, you've now done questions 9 through 16, so we can look at desalination. So desalination is simply the removal of salt from water. So this is a desalination plant in Israel, if I remember correctly, in Ashdod, in Israel. So that's the Mediterranean Sea, which is water that's got loads of salt. It's not safe to drink, it's not potable. Now, what we can do is we can do various processes to get the water away from the salt and just have pure water afterwards. The problem is that it requires a lot of energy. And we use two processes. Process one is distillation, and the second is something called reverse osmosis using membranes, which I believe is essentially you force the water through very narrow straws, and you force it under such high pressure that it kind of leaks out the sides. And the water leaks out the side, but it leaves the salt behind it. It requires a lot of energy. And we'll get to exactly how that works in a second. This here is distillation apparatus, which you've seen now many times in your school career. You do need to be able to describe the simple process of how distillation works. Very straightforward. You boil the water. When it turns into a gas, or at 100 degrees it will turn into a gas, probably a bit before, but it will start turning into a gas. It will rise up out of your flask, up here, and down this glass tube. And here's your thermometer, which when the distillation is going on will be reading 100 degrees centigrade, or thereabouts, and the gas will start to come down this tube. Now what you have is you've basically got a tube inside another tube. So you've got a big tube, and then a small tube running through it, and the big tube has cold water running through it, so you just attach it to a tap. And it's got cold water running through it, and what that does is it cools down this tube. As it cools down the tube, the gas that's inside the tube also cools down, and as the gas cools down, it condenses back into water vapour and can be collected. And at the end of it, you'll have pure water, so water with nothing else in it, in the flask, and you will have all of your salt left over in the distilling flask. Very straightforward. Now, the problem is this requires a lot of energy, as does the other process. So we saw there were two processes, distillation and reverse osmosis. They both require a lot of energy. It makes no sense for a country like England to do desalination because we have water from rivers and from lakes. We have rain, lots of it. It gives us plenty of water that we don't need to do this process in order to make it potable. But if you're in the Middle East, if you're in Saudi Arabia or Israel or Jordan or Lebanon or Syria or wherever, you don't have a lot of water. It's hot and it's dry. You don't have a lot of rivers, you don't have a lot of lakes, you don't have a lot of rain. So you need to try and find a different route. So countries that are on the coast, like Israel or Lebanon or Egypt, would do something like desalination. I think India does it as well. Would do something like desalination because it makes sense for them to do so. Now if you're Syria, you're not going to do desalination because you're not next to the sea. So it's not worth your while. But the countries in the Middle East that have enough money to carry it out and are close enough to the sea are going to be doing desalination. And at this point you can do questions 17 through 24. Let's keep going. That was if we wanted to get clean potable water from rivers, lakes or the sea, or wells. There's another problem, which is that we as humans are covering the planet with factories, with industrial areas that produce waste. And that waste normally ends up somehow in the rivers. And either because it gets pumped there directly or it gets carried there by rain. However it gets there, it ends up in rivers, and that's a bad thing. We're talking about three things here. We're talking about sewage, which is human refuse, so feces and urine. We're talking agricultural wastewater, so water that's got agricultural chemicals in, chemicals that have been used for farming. And we're talking about industrial wastewater, so the wastewater that comes off of factories. This here is a picture of something called eutrophication. This is what happens when you have fertilizer on your fields, because you need your plants to grow nice and big, and it runs off and it gets washed away by the rain and ends up in rivers, and it causes this massive growth of algae and other microorganisms, and basically it ends up with all the fish dying. And the water goes all green, bright green like that. This is from a metal mine in South Africa, somewhere if I remember correctly. And you can see again that colour, and that's going to be all sorts of chemicals that have leaked out from the mine, which people have been using various compounds in order to help with the mining process. Obviously those are both bad things, and once they've happened we need to find a way to treat this water. So sewage and agricultural waste can often have organic matter, so bits of dead plant and stuff like that, but also harmful microbes. Industrial waste can also have the organic matter, but there it can also carry these really harmful chemicals that can kill you. If you consume them, can kill any wildlife if they consume them. There's a nice video there, and I'm going to put these slides on Moodle, so if you want to watch the video you can, but it's not absolutely necessary. Anyway, so how do we treat this water? We have a number of steps. First thing, screening and grit removal. So exactly the same as before when we were trying to make potable water, you just use this big kind of metal frame to get rid of all the big objects, and you can also get rid of some smaller objects like that as well. You then do something called sedimentation, which is basically you leave the water in a big tank and it separates. So any bits of solid sink to the bottom, which leaves just the liquid above it. So you've got all this solid gunk and gunge and slime at the bottom, and you've got this liquid on the top. We call the liquid the effluent, we'll get to that in a second. The bottom stuff, that slimy stuff, is called sewage sludge. What do we do with sewage sludge? We add bacteria to it, and we allow the bacteria to do their job. Basically the bacteria munch on the sewage sludge. It's anaerobic, so we don't provide them with any oxygen, they just munch it themselves and we don't give them any oxygen. You don't need to know any complicated chemical processes here. We need to know biological processes. All you need to know is just anaerobic treatment. And we get two products from that. One we get is biogas. So as they are munching away at this sewage sludge, they are producing biogas. This is a gas that we can burn as a fuel. So we could then bottle that up, put it in a canister and use it for a barbecue, or probably more likely we can add it to the central gas system, and that can come into your house and be used to heat up the water from your boiler or on your hob top or whatever. Anything that's left over we can also use as a fuel, so it's kind of a really thick solid cake, so you can put it out in the sun and it will dry really nicely, and that thick cake again you can use as a fuel, or sometimes I think they even use it as a fertilizer. Anyway, so that's what we do with the sewage sludge. So we've started with sedimentation, we've separated out the sludge on the bottom, that's that slimy gunky stuff, and then the liquid on the top, which we call the effluent. What do we do with the effluent? So the effluent we do aerobic treatment. So we give bacteria, we allow bacteria to have oxygen, and then while they're in there, they're munching away anything that's harmful in there, and then once that's happened we can discharge it back into rivers. Is it safe to drink yet? No, it still would need to be sterilised, but we'd be doing that as other processes, but it is safe to put into rivers. It's not going to cause massive harm to wildlife and local habitats. So there are your steps, which I just spoke about, and you can now do questions 25 to 34. Let's see, should we stop there? Yeah, let's stop there for today.